Welcome to Flourish. I'm Diane Planidin, and you're in the right place if you're ready to create an inspired life. And we do so by working on our own personal development so we can be strong role models for those we love and mentor. Today, we are on chapter 23 in my journey through Psych-100 at Queen's University. And it's quite a bit of information to take in. So I'm chunking it down and I'm keeping it simple so I can absorb as much as humanly possible because my quest is to add this information to a book I'm writing at the moment, and it's part of my research. So I hope you enjoy the journey. And if you're a student, hey, welcome. Welcome to my journey. Let's get started. This is open courseware, and there's a little excerpt in here in the beginning of this chapter on seeing that you'll notice this chapter looks a bit different from earlier chapters. This chapter is from the text Introduction to Psychology, first Canadian edition, versus the other chapters in the past were adapted from the NOBA, N-O-B-A project. But they all have hyperlinks. It's open courseware, so we're good to go. Let's get started. The learning objectives, identifying the key structures of the eye and the role they play in vision, and summarize how the eye and the visual cortex work together to sense and perceive the visual stimuli in the environment, including processing colors, shape, depth, and motion. As mentioned, I am a student, I am not a teacher, and I'm simply sharing my journey as I learn all about it so I can share it with the rest of the world. So let's go. Whereas other animals rely primarily on hearing, smell, or touch to understand the world around them, human beings rely on a large part on vision. A large part of our cerebral cortex is devoted to seeing, and we have substantial visual skills. Seeing begins when light falls on the eyes, initiating the process of transduction. Once this visual information reaches the visual cortex, it is processed by a variety of neurons that detect colors, shapes, and motion, and that create meaningful perceptions out of the incoming stimuli. The air around us is filled with a sea of electromagnetic energy, pulses of energy waves that can carry information from place to place. Electromagnetic waves vary in their wavelength, the distance between one wave peak and the next wave peak, with the shortest gamma waves being only a fraction of a millimeter in length and the longest radio waves being hundreds of kilometers long. Humans are blind to almost all this energy. Our eyes detect only the range from about 400 to 700 billionths of a meter, the part of the electromagnetic spectrum known as the visible spectrum. The sensing eye and the perceiving visual cortex. We have a figure here, and it shows the anatomy of the human eye. You can see light enters the eye through the cornea, a clear covering that protects the eye and begins to focus the incoming light. The light then passes through the pupil, a small opening in the center of the eye. The pupil is surrounded by the iris, the colored part of the eye that controls the size of the pupil by constricting or dilating in response to light intensity. When we enter a dark movie theater on a sunny day, for instance, muscles in the iris open the pupil and allow more light to enter. Complete adaptation to the dark may take up to 20 minutes. Behind the pupil is the lens, a structure that focuses the incoming light on the retina, the layer of tissue at the back of the eye that contains photoreceptor cells. As our eyes move from near objects to distant objects, a process known as visual accommodation occurs. Visual accommodation is the process of changing the curvature of the lens to keep the light entering the eye focused on the retina. Rays from the top of the image strike the bottom of the retina and vice versa, and rays from the left side of the image strike the right part of the retina and vice versa, causing the image on the retina to be upside down and backward. Furthermore, The image projected on the retina is flat, and yet our final perception of the image will be three-dimensional. That's really quite beautiful. Accommodation is not always perfect if the focus is in front of the retina. And we have a new visual here as well. We say that the person is nearsighted, and when the focus is behind the retina, we say that the person is farsighted. Eyeglasses and contact lenses correct this problem by adding another lens in front of the eye, and laser eye surgery corrects the problem by reshaping the eye's own lens. The retina contains layers of neurons specialized to respond to light. The retina, with its specialized cells, is the new figure that we have here coming up. As light falls on the retina, it first activates receptor cells known as rods and cones. The activation of these cells then spreads to the bipolar cells and then to the ganglion cells, which gather together and converge like the strands of a rope, forming the optic nerve. The optic nerve is a collection of millions of ganglion neurons that send vast amount of visual information via the thalamus to the brain. Because the retina and the optic nerve are active processors and analyzers of visual information, it is appropriate to think of these structures as an extension of the brain itself. Rods are visual neurons that specialize in detecting black, white, and gray colors. There are about 120 million rods in each eye. The rods do not provide a lot of detail about the images we see, but because they are highly sensitive to shorter waved, darker, and weak light, they help us see in dim light, for instance at night. Because the rods are located primarily around the edges of the retina, they are particularly active in peripheral vision. Cones are visual neurons that are specialized in detecting fine detail and colors. The 5 million or so cones in each eye enable us to see in color, but they operate best in bright light. The cones are located primarily in and around the fovea, which is the central point of the retina. To demonstrate the difference between rods and cones in attention to detail, choose a word in this text and focus on it. Do you notice that the words are a few inches to the side seem more blurred? This is because the word you are focusing on strikes the detailed-oriented cones, while the words surrounding it strike the less detail-oriented rods, which are located in the periphery. Margaret Livingstone in 2000 found an interesting effect that demonstrates the different processing capacities of the eyes, rods, and cones. Namely, that the Mona Lisa smile, which is widely referred to as elusive, is perceived differently depending on how one looks at the painting. Because Leonardo da Vinci painted the smile in low detailed brushstrokes, these details are better perceived by our peripheral vision, the rods, than by the cones. Livingston found that people rated the Mona Lisa as more cheerful when they were instructed to focus on her eyes than they did when they were asked to look directly at her mouth. As Livingston put it, she smiles until you look at her mouth and then it fades like a dim star that disappears when you look directly at it. As you can see in the next figure, if you're watching this on YouTube, the pathway of visual images through the thalamus and into the visual cortex. The sensory information received by the retina is relayed through the thalamus to corresponding areas in the visual cortex, which is located in the occipital lobe at the back of the brain. Although the principle of contralateral control might lead you to expect that the left eye would send information to the right brain hemisphere and vice versa, nature is smarter than that. In fact, the left and right eyes each send information to both the left and the right hemisphere, and the visual cortex processes each of the cues separately and in parallel. This is an adaptational advantage to an organism that loses sight in one eye, because even if only one eye is functional, both hemispheres will still receive input from it. The visual cortex is made up of specialized neurons that turn the sensations they receive from the optic nerve into meaningful images. Because there are no photoreceptor cells at the place where the optic nerve leaves the retina, a hole or blind spot in our vision is created. When both of our eyes are open, we don't experience a problem because our eyes are constantly moving and one eye makes up for what the other eye misses. But the visual system is also designed to deal with this problem. If only one eye is open, the visual cortex simply fills in the small hole in our vision with similar patterns from the surrounding area, and we never notice the difference. The ability of the visual system to cope with the blind spot is another example of how sensation and perception work together to create meaningful experiences. Perception is created in part through the simultaneous action of thousands of feature detector neurons, specialized neurons located in the visual cortex that respond to the strength, angles, shapes, edges, and movements of a visual stimulus. The feature detectors work in parallel, each performing a specialized function when faced with a red square. For instance, the parallel line feature detectors, the horizontal line feature detectors, and the red color feature detectors all become activated. This activation is then passed on to other parts of the visual cortex, where other neurons compare the information supplied by the feature detectors with images stored in memory. Suddenly, in a flash of recognition, the many neurons fire together, creating the single image of the red square that we experience for an explanation about the Necker cube. And we have an illustration here. The Necker cube is an example of how the visual system creates perceptions out of sensations. We do not see a series of lines, but rather a cube. Which cube we see varies depending on the momentary outcome of perceptual processes in the visual cortex. You have to look at this cube, it's quite fascinating. All right. Some feature detectors are tuned to selectively respond to particularly important objects, such as faces, smiles, and other body parts. When researchers disrupted face recognition areas of the cortex using the magnetic pulses of transcranial magnetic stimulation, people were temporarily unable to recognize faces, and yet they were still able to recognize houses. Perceiving color. It has been estimated that the human visual system can detect and discriminate among 7 million color variations. But these variations are all created by combinations of the three primary colors, red, green, and blue. The shade of a color, known as a hue, is conveyed by the wavelength of the light that enters the eye. And we detect brightness from the intensity or height of the wave. In his important research on color vision, Hermann von Helmholtz theorized that color is perceived because the cones in the retina come in three types. One type of cone reacts primarily to blue light, short wavelengths. Another reacts primarily to green light, medium wavelengths. And a third reacts primarily to red light, long wavelengths. The visual cortex then detects and compares the strength of the signals from each of the three types of cones, creating the experience of color. According to this young Helmholtz trichromatic color theory, what color we see depends on the mix of the signals from the three types of cones. If the brain is receiving primarily red and blue signals, for instance, it will perceive purple. If it is receiving primarily red and green signals, it will perceive yellow. And if it is receiving messages from all three types of cones, it will perceive white. The different functions of the three types of cones are apparent in people who experience color blindness, the inability to detect green and or red colors. About 1 in 50 people, mostly men, lack functioning in the red or green sensitive cones, leaving them only able to experience either one or two colors. The trichromatic color theory cannot explain all of human vision. However, for one, although the color purple does appear to us as a mix of red and blue, yellow does not appear to be a mix of red and green. And people with color blindness who cannot see either green or red, nevertheless, can still see yellow. An alternative approach to the Young-Hemlops theory, known as the opponent process color theory, proposes that we analyze sensory information not in terms of three colors, but rather in three sets of opponent colors: red, green, yellow, blue, and white, black. Evidence for the opponent process theory come from the fact that some neurons in the retina and in the visual cortex are excited by one color, for example, red, but inhibited by another color, for example, green. One example of opponent processing occurs in the experience of an after image. If you stare at the shape on the top left side, you have a new figure here, for about 30 seconds. The longer you look, the better the effect. And then move your eyes to the blank area to the right, you will see the after image. Now try this by staring at the image of the Italian flag below and then shifting your eyes to the blank area beside it. Okay, you're going to have to watch this on YouTube. This is too fascinating. When we stare at the green stripe, our green receptors habituate and begin to process less strongly, whereas the red receptors remain at full strength. When we switch our gaze, we see primarily the red part of the opponent process. Similar processes create blue after yellow and white after black. The tricolor and the opponent process mechanisms work together to produce color vision. When light rays enter the eye, the red, blue, and green cones on the retina respond in different degrees and send different strength signals of red, blue, and green through the optic nerve. The color signals are then processed both by the ganglion cells and by neurons in the visual cortex. Perceiving form. One of the important processes required in vision is the perception of form. German psychologists in the 30s and 40s, including Max Wertheimer, Kurt Kafka, and Wolfgang Kohler, argued that we create forms out of their component sensation based on the idea of the Gestalt, a meaning of organized whole. The idea of the Gestalt is that the whole is more than the sum of its parts. Some examples of how Gestalt principles led us to see more than what is actually there are summarized, and they have another table here, table 1, 5.1. I am going to try and go through this table for you. Principle, figure and ground. Description, we structure input so that we always see a figure, image, against a ground, background. Example, at the right you may see a vase or you may see two faces, but in either case you will organize the image as a figure against the ground. So the white portion looks like a vase and the black portion looks like two faces looking at each other. Similarity. Stimuli that are similar to each other tend to be grouped together. You're more likely to see three similar columns among the XYX characters at the right than you are to see four rows. So they have a 3x4 graph here with all X's and Y's vertically rather than seeing the rows. Proximity. We tend to group nearby figures together. The question is, do you see 4 or 8 images at the right? The principles of proximity suggest that you might only see 4. So there's actually 8 dots, but they're in groups of 2. So it looks like you're seeing 4 instead of 8. Continuity. We tend to perceive stimuli in smooth, continuous ways rather than in more discontinuous ways. So at the right, most people see a line of dots that moves from the lower left to the upper right rather than a line that moves from the left and then suddenly turns down. The principle of continuity leads us to see most lines as the following the smoothest possible path. Closure. We tend to fill in gaps in an incomplete image to create a complete whole object. Closure leads us to see a single spherical object at the right rather than a set of unrelated cones. So they have all of these cones and that's it. But we fill in the blank and all of a sudden it looks like a round white ball with all of these pointers sticking out of them. All right, hopefully that helped. Depth perception is the ability to perceive three-dimensional space and to accurately judge distance. Without depth perception, we would be unable to drive a car, thread a needle, or simply navigate our way around the supermarket. Research has found that depth perception is in part based on innate capacities and in part learned through experience. Psychologists Eleanor Gibson and Richard Walk in 1960 tested the ability to perceive depth in 6 to 14-month-old infants by placing them on a visual cliff, a mechanism that gives the perception of a dangerous drop in which infants can be safely tested for their perception of depth. The infants were placed on one side of the cliff while their mothers called to them from the other side. Gibson and Walk found that most infants either crawled away from the cliff or remained on the board and cried because they wanted to go to their mothers, but the infants perceived a chasm that they instinctively could not cross. Further research has found that even very young children who cannot yet crawl are fearful of heights. On the other hand, studies have also found that infants improve their hand-eye coordination as they learn to better grasp objects and as they gain more experience in crawling, indicating that depth perception is also learned. Depth perception is the result of our use of depth cues, messages from our bodies and the external environment that supply us with information about space and distance. Binocular depth cues are depth cues that are created by retinal image disparity, that is, the space between our eyes, and which thus requires the coordination of both eyes. One outcome of retinal disparity is that the images projected on each eye are slightly different from each other. The visual cortex automatically merges the two images into one, enabling us to perceive depth. Three-dimensional movies make use of retinal disparity by using 3D glasses that the viewer wears to create a different image on each eye. The perceptual system quickly, easily, and unconsciously turns the disparity into 3D. An important binocular depth cue is convergence, the inward turning of our eyes that is required to focus on objects that are less than about 50 feet away from us. The visual cortex uses the size of the convergence angle between the eyes to judge the object's distance. You'll be able to feel your eyes converging if you slowly bring a finger close to your nose while continuing to focus on it. When you close one eye, you no longer feel the tension. Convergence is a binocular depth cue that requires both eyes to work. The visual system also uses accommodation to help determine depth. As the lens changes its curvature to focus on distance or close objects, information relayed from the muscles attached to the lens help us determine an object's distance. Accommodation is only effective at short viewing distances. However, so while it comes in handy when threading a needle or tying a shoelace, it is far less effective when driving or playing sports. Although the best cues to depth occur when both eyes work together, we're able to see deeply even with one eye closed. Monocular depth cues are depth cues that help us perceive depth using only one eye, hence mono. Some of the most important are summarized. Here we have yet another table. Molecular depth cues that help us judge depth at a distance. So position. We tend to see objects higher up in our field of vision as farther away. For example, The fence posts at the right appear farther away, not only because they become smaller, but also because they appear higher up in the picture. Relative size. Assuming that the objects in a scene are the same size, smaller objects are perceived as farther away. At right, the cars in the distance appear smaller than those nearer to us. Linear perspective. Parallel lines appear to converge at a difference. We know that the tracks at the right, like they have an example of train tracks here, are parallel. When they appear closer together, we determine they are further away. Light and shadow. The eye receives more reflective light from objects that are closer to us. Normally, light comes from above, so darker images are in shadow. We see the images at the right as extending and indented according to their shadowing. If we invert the picture, the images will reverse. And interposition. When one object overlaps another object, we view it as closer. At right, because the blue star covers the pink bar, it seems closer than the yellow moon. And aerial perspective. Objects that appear hazy or that are covered with smog or dust appear further away. And it says here, the artist that painted the picture on the right uses aerial perspective to make the clouds more hazy and thus appear further away. Perceiving motion. Many animals, including human beings, have very sophisticated perceptual skills that allow them to coordinate their own motion with the motion of moving objects in order to create a collision with that object. Bats and birds use this mechanism to catch up with prey. Dogs use it to catch a frisbee, and humans use it to catch a moving football. The brain detects motion partly from the changing size of an image on the retina. Objects that look bigger are usually closer to us, and in part from the relative brightness of objects. We also experience motion when objects near each other change their appearance. The beta effect refers to the perception of motion that occurs when different images are presented next to each other in succession. The visual cortex fills in the missing part of the motion, and we see the object moving. The beta effect is used in movies to create an experience of motion. A related effect is the phi phenomenon, in which we perceive a sensation of motion caused by the appearance and disappearance of objects that are near each other. The phi phenomenon looks like a moving zone or cloud of background color surrounding the flashing objects. The beta effect and the phi phenomenon are other examples of the importance of the gestalt, our tendency to see more than the sum of its parts. The beta effect and the phi phenomenon. In the beta effect, our eyes detect motion from a series of still images, each with the object in a different place. This is a fundamental mechanism of motion pictures. In the phi phenomenon, the perception of motion is based on the momentary hiding of an image. Key takeaways. Vision is the process of detecting the electromagnetic energy that surrounds us. Only a small fraction of the electromagnetic spectrum is visible to humans. The visual receptor cells on the retina detect shape, color, motion, and depth. Light enters the eye through the transparent cornea and passes through the pupil at the center of the iris. The lens adjusts to focus the light on the retina, where it appears upside down and backward. Receptor cells on the retina are excited or inhibited by the light and send information to the visual cortex through the optic nerve. The retina has two types of photoreceptor cells: rods, which detect brightness and respond to black and white, and cones, which respond to red, green, and blue. Color blindness occurs when people lack function in the red or green sensitive cones. Feature detector neurons in the visual cortex help us recognize objects, and some neurons respond selectively to faces and other body parts. The young Helmholtz trichromatic color theory proposes that color perception is the result of the signal sent by the three types of cones, whereas the opponent process color theory proposes that we perceive color as three sets of opponent colors: red, green, yellow, blue, white, black. The ability to perceive depth occurs as the result of binocular and monocular depth cues. Motion is perceived as a function of the size and brightness of objects. The beta effect and the phi phenomenon are examples of perceived motion. Well, that was a lot to take in. I'm just going to say, I really hope you're watching this on YouTube so you can see the visuals. It really makes a difference to understand the big picture. And hey, if you like the show, share it with someone you know and hit that subscribe button. We are all here to serve one another wherever you are in the world. I want you to succeed in this class. I want to succeed in this class. And I thought I'm going to share my journey because it's open courseware. And I want to try and inspire others to keep going. You've paid a lot for this course. You deserve to win, pass, succeed, and live a more inspired life. I'll see you in the next episode.